Hey guys, so we're going to cover some of the highlights from solutions that we won't get to this year. So some of this should be a review from physical science. Remember, we have the words solute and solvent, and when we put them together, we make a solution. So our solvent, it is what is doing the dissolving. It's usually a liquid, not always. And then our solute is what is being dissolved. And so this can be a solid. We can also have gas as our solute and even liquids. That's how we get like carbonated water or like the CO2 in our sodas because it's dissolved CO2. So in that case, the carbon dioxide is the solute. But we have two things basically that we're putting together, and that's what's making our solution. Okay, there's a couple words that are probably new, but that are dealing with describing solutions and what's happening. One of these words is solvation. Okay, so this is the idea that our solvent molecules are going to surround our solute particles, and that's what's making something dissolve in it. Here we have sodium, a sodium ion, so this is probably like sodium chloride, so think salt being added to water. It dissolves because the water particles surround or they aggregate, they clump up around each of the particles. And that's called solvation. And that's what's allowing it to dissolve. It's because it's surrounding each individual particle. So we don't have a bunch of sodium atoms all together. We have each sodium atom is surrounded by water atom or water molecules. So that's the idea of solvation. We also have the idea of dissociation, and this is dealing when we have mostly ionic compounds. So when we have salt, for example, and we put it into our water, what's going to happen in order for that solution to occur and to have this solution is that first we're going to have dissociation, which is the separation of that sodium chloride into two different species, the cation and the anions. So when we have things that are ionic bonds made of ions, when we put them into water, that partially negative and partially positive regions of our water molecule are going to help break apart the sodium and the chlorine ions so that they are separate. So this is different than the idea of solvation because that's the surrounding of the ion by the water molecules. Dissociation is when it's breaking apart and separating those two ions, the sodium and the chlorine. This picture is showing both dissociation and solvation. The dissociation is the sodium chloride being separated, and the solvation are the water molecules aggregating around each of the ions. So those are two concepts that are how we describe and think about solutions. Some other really cool things about solutions is we get something called freezing point depression. So this is the idea that if we add solutes to our solution, that it's going to lower the freezing point normally. A great example of this, which we don't get too often down here, but when it gets really cold out and we're starting to get freezing temperatures, sometimes people will put salt on roads or walkways. This is because that salt we are adding to the solution, it is lowering the freezing point of water. So the water would not freeze at 0 degrees Celsius anymore. When we add the salt, it now freezes lower than that. So the idea behind that is that the if it's around 0 degrees, everywhere that you put salt is not going to freeze yet because it's not cold enough to freeze. So that's something that's kind of cool and is a very helpful aspect of solutions. Another example of this is we actually also have boiling point elevation. So freezing point goes down if we add solute. Boiling point though goes up. So this is behind the idea of why we add salt to water when we're going to boil and make pasta or something. A lot of times people think that you're adding the salt because it's going to make the water boil faster, but that's actually not correct. What you're actually doing when you add the salt is that you're making the boiling point go up. So you can see here, this is showing the water here is being surrounded by its happy little friends, and which are the solutes, and it's saying that it's making it harder for them to reach my boiling point. So they have to get to a higher temperature. So the reason this is helpful in cooking is that if you have water without salt in it, it's going to boil at 100 degrees Celsius every time. But if you add salt, the water is going to take a little bit longer actually to boil, but when it boils, it's not at 100 degrees. It's going to be higher than 100 degrees, which means our water is hotter, and then we can cook things faster. So that's the idea behind boiling point elevation and why we put salt into water to help it boil. It doesn't actually help it boil, it helps us cook our food faster because the water is hotter. Okay, we can also deal with acids and bases in solutions. It's a big thing that we deal with when we're talking about solutions. And so the first thing I want to talk about is our nomenclature of acids. Bases don't really get any special nomenclature. Remember, nomenclature is our names. But acids do, and I didn't talk about this when we talked about nomenclature before because I felt like it was a lot of information we were dealing with all at once, and so I wanted to wait and introduce it because it's not a whole lot more difficult, just a couple extra rules. So the big thing to keep straight with acid nomenclature is there's two different kinds of ways you can name things. And one is dealing with things with oxygen, and this is going to be particularly our polyatomic ions. So there's a polyatomic ion with oxygen. We're going to use these rules down here. If there's not, we will use the rule up here. And the rule is we turn whatever the thing is that's "-ide", we add hydro in front, say the name of the atom, and then instead of "-ide" at the end, we're going to say "-ic", and then say acid. When we have a polyatomic ion, there's going to be two endings that polyatomic ion has, ate or ite. You can think like chlorate and chlorite, or phosphate and phosphite. And what we do is we don't continue to say the ate and the ite at the end. If it's an ate and it's an acid, we turn it into "-ic" and then add acid at the end. And the way that is easy to help us remember that is if we ate something, if we ate an acid, it's going to make us say "-ic". So ate, and then we go "-ic". If it's ite, we're going to change the ending to "-ous", so us, acid. So we'll do some examples of this so it makes a little more sense. So this first one up here is an acid that's pretty common, HCl. And so we can see right off the bat when we looked at our rules, we have with oxygen or no oxygen. This does not have oxygen. So we're going to use this first rule where we change the "-ide. We put hydro, the stem, "-ic", acid. So this is going to start with hydro. And so the stem for this is going to be our chlorine ion, which normally we would write this as hydrogen chloride. But because it's an acid and we're following this rule, it's not going to be chloride. We're going to call it hydrochloric and then add acid at the end. And so we put that all together and we have hydrochloric acid. Okay, this next one does have oxygen in front, and we need to look at our polyatomic ions if we don't remember our polyatomic ions. So remember, I have this posted on Canvas if you need it. So H2SO4. So if we look for SO4, we see that SO4 is sulfate. So normally we would maybe think to name this as hydrogen sulfate, but it is an acid. So what we are going to do instead is it ends in "-ate". So we're going to take the hydrogen off. And "-ate", we ate the acid and we said "-ic". We're going to change the "-ate" to "-ic" and then add acid. So this is we actually say sulfuric acid. So we add a couple letters to make it easier to say. This next one is no oxygen, so it's going to follow the same rules as our hydrochloric acid. So it would be hydro, and then this will be sulfur, but instead of writing sulfide like we would normally when we're naming, we're going to say hydrosulfuric acid. Okay, this next one, H2SO3. So we have oxygen, we got to look at our polyatomic ions. SO3 is sulfite. So we might think this would be hydrogen sulfite, but it's an acid. So we're going to take off that hydrogen. Ite becomes OUS. And this one is sulfurous acid. And then one more we're going to do together is HNO3. We look on our polyatomic ion. NO3 is nitrate. So that 8 is going to become ic. So this one is nitric acid. So just a couple extra rules that you have to remember when you're naming acids. Okay, we can think about acids in a couple different ways. We can call them Arrhenius acids and bases. This is kind of the first definition we had of acids and bases. And this idea is that acids add hydrogens to the solution and that bases add hydroxides, OH, to the solution. And I probably should put that this is a hydrogen is H plus, and our hydroxide is also an ion, which is OH minus. So if we had some water here, right off the bat, it doesn't have any extra hydrogens, so it's going to be neutral. But if we add some HCl, some hydrochloric acid, what's going to happen is that HCl is going to dissociate, so it's going to break apart, and then we now have chlorine atoms floating around, but we also have hydrogen ions floating around. So because of that, it has donated, we have extra hydrogen ions floating around, making it an acid. And what actually happens is those hydrogens don't just stay hydrogens all by themselves, they actually bond to water molecules and form something called a hydronium ion. So sometimes you'll see when we're talking about acids, you'll see it written as a hydrogen ion. And sometimes you'll see it written as a hydronium ion. It's really showing the exact same thing. Probably drawing it as a hydronium ion would be more accurate because that's what's actually happening in the solution. It's not staying like this. With the hydrogen, it's turning into hydronium pretty rapidly. Okay, so that's the idea behind our acids. Our bases are going to be kind of the opposite when we're dealing with this definition of this model of acids and bases. So we have water and we add a base like sodium hydroxide here. It's going to dissociate. We now have sodium ions floating around and we have hydroxide ions floating around. And so because it was donating OHs to the solution, hydroxides to the solution, it's a base because of that. Okay, this is one model that they use to describe acids and bases, but they realized that this doesn't always isn't the best way to describe it because we can have things that act as bases even though they don't have hydroxides that they're adding to the solution. So this was one scientist's way of describing acids and bases, but it's a model and it has some faults. So the next model we're going to talk about is the Bronsted-Lowry acids and base model. Half of it is very similar. The acids, it's very similar, is that hydrogens are being donated if it's an acid. So again, our hydrochloric acid, if we add it to our solution, we're going to have chlorine ions, and now we have hydrogen ions that are forming hydronium ions with our water. Still an acid, still the same idea. It has to be making and adding hydrogens. However, Bronsted-Lowry described bases differently, and then that they don't just have to have hydroxides that they're adding. It can also be a base if it's just simply accepting hydrogens. So you can kind of think about this if we add hydrochloric acid and we now have chlorine ions and hydrogen ions floating around. But what if we were to add an ion or like a different ion, or you could add a chlorine ion, it can then bond to the hydrogen ions that are already there. So just because it's an OH, it's not an OH doesn't mean it can't also bond to this hydrogen, making it pretty much, you can kind of think of it as like taking the hydrogen out of play. If it's bonded, it can't interact or react with any other thing, which is the idea behind acids and bases. Okay, so a concept that's related to acids and bases is pH, which you've probably heard of before. The pH scale goes from 0 to 14, with our smaller numbers being our acids and our bigger numbers being our bases. The closer to those two extremes that you get, the stronger the bases, and the closer towards 7 we get, the weaker the acid or weaker the base, with 7 being neutral. So we won't be doing too many calculations with this, but there are several ways that you can do calculations. So I kind of wanted to just glance over some of the ideas behind that with pH. And the big thing is what pH is actually standing for is pH is the negative log of the concentration of the hydrogen ions in the solution. So whenever you see this bracket symbol, that's usually talking about concentration of whatever's inside of the bracket. So this is saying the negative log of the concentration of our hydrogen ions. So that's how we can tell the properties of how strong or weak an acid is proportional to how many extra hydrogen ions we have floating around in our solution. If we have a lot of hydrogen ions floating around in our solution, then we're going to have a really low pH, and that is shown by when we do the negative log of the concentration. If we don't have very many hydrogen ions, it's going to make our pH larger. We can also do the same exact type of calculation, though, instead of looking at our hydrogen ions, looking at our hydroxide ions if we have a base that we're looking at with hydroxides. So that would be called the POH, which is something that we can calculate. You don't normally think about it as much being calculated because it's describing bases more, but you can really use pH or POH to describe either acids or bases. They're just kind of the opposites of each other. But if you take the pH of a solution, the negative log of the concentration of hydrogen atoms, and you add it to the pH, or the POH, which is the negative log of the hydroxide ions, it should equal 14. So if we're adding up how many hydrogens we have and how many oxygens we have, and we added the pH and the POH, it should be 14. So this can be helpful in determining how many, what the concentration of each of these ions is. If you know how many hydrogen ions there are, you can then use this equation to figure out the POH and then calculate how many hydroxide ions, or vice versa. So we won't be doing examples like this right now, but this is just something to keep in mind, that if you take chemistry in the future in college, that they will probably have you doing calculations like this. Okay, another idea behind acids and bases is neutralization. So neutralization reactions is when we have an acid and we have a base and we put them together, we will have a reaction. This is like the a pretty common reaction that we have. So it's like baking soda and vinegar is a neutralization reaction, where we have an acid, our vinegar, and our base is the baking soda, and they react. And after the reaction is over, you would be left with a salt and water. So the idea behind this is that when we're adding our acid and base, they neutralize each other. So we're not left with an acid, we're not left with a base, we're left with neutral water. And whatever was bonded to the acid and bonded to the base, that's what forms our salt. So this is a neutralization reaction. But you have to also keep in mind that this the final solution in this will be neutral only if you use the correct amount of acid and base. For instance, what if you had a lot of acid and then not very much base that you're adding? So because of that, as much base as you have will neutralize the acid, but because the base in this case would be the limiting reactant, you would have a bunch of excess acid left over that is unreacted, and so therefore your final solution would be acidic. So the biggest thing for instance, this neutralization reactions are really important if you have an acid spill. Like you spill some really concentrated acid on the floor, you don't want to just start sweeping it up or whatever, because that can start corroding different materials. So first you have to neutralize it. So you would just keep adding base to the solution until the reaction is stopped and there's no more reaction happening, which tells you then that everything has been neutralized to water. So this is the idea behind our neutralization reactions. We can also use this idea of neutralization reactions to actually calculate and figure out the concentration of acids if we don't know the concentration of an acid. And this is called something called a titration. So if we have a concentration of acid down here that's unknown, and we can then make a solution of base that we do know. So we have a known concentration and an unknown amount of base. And what we would do is we would add a pH indicator to our solution, something that's going to change color when it reaches a certain pH. And you add, you have something called a stopcock, which is like a little turn thing. You can kind of see it up here in this image, but it's going to allow you to only add 1 drop at a time to your solution. So as you do that and you're mixing the solution, each drop that goes into your solution, each drop of base is neutralizing some of the acid. And then as you're mixing it around, it's able to interact with all of the molecules inside of your flask. But it's gonna not really change the pH of your concentration a whole lot because you're only adding 1 drop. So the idea is that you keep adding base little by little, and you can keep track of how much base you're actually adding so that you can see when it changes color, that is at a particular pH. So it tells you, you can then figure out, okay, if I added this much base to my solution and then it changed to this pH, you can then calculate the concentration of the acid that you had that was unknown. So this is a pretty common experiment that can be used in procedure to figure out the concentration of an unknown acid. And this would be pretty common. You will definitely probably be doing experiments with titrations in college if you do chemistry there. Okay, something else that we use to describe solutions is molarity. So molarity is a way we can describe how concentrated a solution is. And so it's a number that we calculate by doing the moles of our solute divided by our liters of our solution. So for example, if we have really, really concentrated hydrochloric acid, like the hydrochloric acid you get from a supplier that sells chemicals, and it's the most concentrated acid you could get, that would be like 12 molar hydrochloric acid. So we use that to describe how many moles of HCl there are in the water that's in the solution. Well, that would the liters of the solution. So, but we can also have more dilute hydrochloric acid, because there's very, very few times I've ever heard of anybody using fully concentrated 12 molar HCl for any sort of reaction. You just use it that way because it's easier to store. You don't have to store as much of the solution or as much of the acid as you would if you had a dilute amount. So you can then take this 12 molar and make your own solutions and dilute it so that it's a different molarity that is more reasonable to work with, because you don't want to work with too strong of an acid if you don't have to. And so if you're working with like 1 molar hydrochloric acid or even 0.5 molar hydrochloric acid, it's going to be less strong. It's still hydrochloric acid and still working the same way. It's just not the concentrated amount that it would be at 12 molar. Okay, and so in order to calculate how much we would have to add to get a specific molarity, we can do something called dilutions, where we dilute our sample so that it is a particular molarity that we want. And we're basically doing a ratio when we're doing these calculations. And this is a pretty handy and helpful calculation. is M1V1 equals M2V2. So this equation is telling us M1, the molarity 1 times the volume 1 equals the molarity 2 times the volume 2. Sometimes you might see this instead of M1V1, you'll see it as C1V1 equals C2V2, and that in that case the C is standing for concentration. It's the same idea. So what we're doing here is we're wanting the molarity, so how strong or how concentrated our starting thing is, going to how concentrated our final solution is, and then our V is the volume, so the volume that we are starting from and the volume that we're ending from. So we will do a couple examples of these. Okay, so in this example it says, how would you make 1 liter of 1 molar hydrochloric acid if you had 6 molar stock solution? And a stock solution is the solution that you're starting from that you will then make your own solutions from. Okay, so that means our starting solutions are going to be the M1, and our ending solution is the thing we are making. So in this case, our 1 liter of 1 molar hydrochloric acid is what we're making. So that's going to be our M2 and our V2. And then our 6 molar is our stock solution. So that's going to be what we're starting with. Okay, so our M1 is going to be our 6 molar times our V2 we don't know yet. And then our M2, the molarity that we want, is 1 molar times our volume 2. We want to make a final volume of 1 liter. So what we would do now, one thing to make sure that you keep in mind is that your units are the same on either side. So that means whatever volume we're looking for, it's going to be given in liters. So that means in order to find V2, we need to divide each side by 6 molar. So that this 6 molar cancels with this 6 molar. So we're doing 1 times 1 divided by 6 to give us 1.6 repeated. So this only has really one sig fig that we're given. So I'm going to just say 0.2 liters. Okay, so what does this number mean? So that means if we are going to make a solution, let me put this off to the side. Okay, it says we are starting with a 6 molar stock solution. So if that is our stock solution, we want to take some of that and put it in our own solution that is going to be 1 molar. So that means we're using 0.2 liters of the beginning thing. So that means we're going to not use all of what we have. We're going to take 0.2 liters of it and we're going to add it to our solution. And then we can then fill the rest of it with water until we get to 1 liter, which is our final volume. So that's how this solution, how you would make it. One thing, I guess, for safety that we would do, because this is dealing with hydrochloric acid, for safety purposes, when you are making solutions with acid, you always add acid to your water. So A for add, A for acid. You add acid to the water. You don't add water to the acid. And the reason is because if you have an acid sitting in the bottom of your beaker and you add some water to it, what's going to happen is you're going to make splashes. And that means you could have concentrated acid that is now splashing up and could get onto you, your skin, your clothing, and then it could damage or corrode the things it touches. So what you're going to do is first you're going to add some water to your beaker, then you will add your acid to it, so then it dilutes the acid. If you need to add a little bit extra water at the end to top it off so it's the right volume, then you can. So it's just a little bit of safety behind how we make solutions with acids. But we still just use this simple equation, which is really just looking at it's like a ratio to figure out how much we're going to add to make our solutions. We'll do one more example of this. Okay, how could 100 milliliters of 0.125 molar H2SO4, so sulfuric acid solution, be made from 0.5 molar sulfuric acid solution? So we're wanting to make, how could 100 mils, we're wanting to make this right here. So that means that's going to be our final. So that's going to be the 2's. Because that's what we want to make. And the thing we are making it from is 0.5 molar H2SO4. So that's going to be this one. So we can go ahead and start with that 5 molar times our V1 equals 0.125 molar times 100 milliliters. And then we just solve for V1. This cancels. We're left with V1. We're going to do in our calculator 0.125 times 100 divided by 0.5, which is 25. And we are going to use 3 sig figs because everything here has 3 sig figs. So we will write that as 25.0. And in this case, we canceled our moles or our molarity units or molar units, so we're left with milliliters. So that's one thing I really want you guys to take away from doing calculations in chemistry is that units are your friend. If you ever forget even the equation that you're supposed to be using, as long as you are keeping track of your units and canceling your units, it will tell you what unit you're supposed to have at the end, which is very, very helpful. So that our molar units canceled and we're left with milliliters. So that means we're going to, how we would make that actual solution is we have a 0.500 molar solution, and we're taking from that 25 mils, and we're going to put that into our container, probably a volumetric flask, but anyway. And then we are wanting to make 100 mils of it. So that means we need to add 75 mils of water so that the whole thing is at 100 mils. So like approximately 75 mils of water. How you would actually make the solution is you would probably add about 70 mils or so of it. And then you'd add 25 mils of your acid, because remember we add acid to water, and then you can add a little bit on top until it gets to the 100 mil mark so that you know it's at the right solution. So we would then need to label, because making sure that our acids in our different beakers are labeled properly is very important. So you could then label your solution as 0.125 molar H2SO4 so that somebody else could know not only what is in that glassware but also how concentrated it is. So I hope this was helpful, kind of giving you an overview of solutions and acids and bases so you can get an idea of the types of things you'll be learning in chemistry if you continue into college.